Hi, next are the negative binomial and the hypergeometric random variables. The setup for the negative binomial random variable is waiting for the R's success in a sequence of independent trials. So in fact we have two parameters, R and P. These are the two parameters. R is a positive integer, P is a probability, and we have an infinite sequence of independent trials. I'm just going to say IID trials of success probability P. So we have this infinite sequence of trials, and so far the setup is the same as the geometric, the optimistic geometric actually. And so we're waiting for the R success in this infinite sequence. So let me draw a little picture here. Here are the trials, first, second, and so on. Okay, and here we have a failure, and a failure again, and then we have a first success. So this is a success, and maybe the second success straight away here, following, and then a failure, and so on and so on. So this is going to be the first success, this is going to be the second success, and there are some more failures, and eventually the R's time, we're happy. This is the R's success. Then we measure the total number here. So I'm going to draw it like that. We measure how many trials we had to do. This is what we're going to call X, and this is going to have this random number will have the negative binomial random distribution. Okay, so this is negative binomial. Now, what is the smallest value this thing can be? Well, we're waiting for the R success, and we do it in a kind of an optimistic sense, in the sense of optimistic and pessimistic geometry. We're looking at successes, not failures. So if we're waiting for the R success, then clearly we need at least R trials. So the smallest X can be is R, but then it can be any number above that, equal or above that. And of course there is no bound, because it could be very large. So there is no bound on what R can be. Now it's a bit more interesting to find out the mass function value, the probability that X is K. Clearly it's only interesting for K at least R. If K is smaller than R, then of course this is 0. And so how can it be that we need exactly K? How can it be that this distance is K? We need exactly K trials to see the R's time a success. So what is going to happen is that I'm going to redraw my picture. And so this is the first trial, the second trial, the third, and so on. And this is going to be the R's trial. And in the R's trial, of course, we see our success. So we're very happy here. Now, before the R's trial, in this event that X is K, we have K minus 1 trials before that. So X equals to K. To the R success, we have K trials. So this one is the case, the R's trial. No, this should be, so apologies. This should be the case trial, and this should be the R's success. Okay, so we're looking at a total of K trial on which we see the R's success. And beforehand, we have K minus 1 trials, and somewhere are distributed in here a total of R minus 1 successes, somehow distributed. Okay, there is going to be in these k-1 spots, there is going to be in any order r-1 successes and all the remaining k-1 minus r-1 failures. So let me write this out again. In this k-1 slots, we're going to have r-1 successes, and we are going to have k-1 minus r-1, or just k minus r failures. And these can occur in any particular order. Whatever order these occur, it will lead to exactly this event, that the R's success comes on the case trial. Okay? Now, what is the probability of seeing all this configuration? What is the probability of all that? So this whole event, which I try to illustrate here, this whole event is the event that x equals to k, so the R success comes on the case trial. What is the probability of this whole thing? So again, what is the probability that x is equal to k? So what is the probability of this whole event? Now, any particular order of this whole sequence up to k, any particular order will have probability q to the k minus r and p to the k. And that's because we have k minus r failures independently occurring, each happens with probability q, and we have, and this is not k, this is r, apologies, this is r. So we have k minus r failures occurring in some order. We have a total of r successes, because this is the r success. We have r minus 1 here and the last one. So that's a total of r successes, k minus r failures. And we want this to be in any order among the first k minus 1 trials, except that the case 1 must be a success. So we're fixing the last success. In the previous k minus 1 trials, we have r minus 1 successes and k minus r failures. How many ways are there to arrange them? The number of ways is, of course, k minus 1 choose r minus 1. This is how many ways we can make an order in the first k minus 1 slots of the r minus 1 successes and the k minus r failures. Okay? And therefore, each of these orders counts, each of these orders is separate in this probability space. So therefore, this event that we have r minus 1 successes and the last one is also a success, in any order here, is occurring with that probability. That this thing is a mass function, I'm not going to prove it. It is going to come later on in a later video. That's a non-trivial fact. And it actually works, but it's not so easy. Another remark I want to make here is a very important observation. Namely, if you look at the distance between, well, the distance until the first success, notice that this is the first success. This distance here, this random number of trials needed until the first success, is going to be what I call y1. Then the number of trials before the next success, so after that, the number of the waiting time, the number of trials needed to see the next success, I'm going to call y2. Then somewhere in here there's going to be another success. The waiting time between the consecutive successes is going to be the sequence of the y's. And then somewhere there might be some more successes depending on the value of r. The waiting time for the last success after the one before that is going to be yr. Okay? And if you look at this picture carefully, then you notice that y1 is an optimistic geometric, y2 is an optimistic geometric, y3 and so on up to yr are all optimistic geometrics, and these y's are independent of each other. We're looking at independent trials, so the waiting time before consecutive successes are of course independent random variables, and they are each geometric. So a very important point to notice here is that x has the same distribution as the sum of r independent optimistic geometrics. So the yi's are IID optimistic geometrics of parameter p, which parameter p is the same as the parameter of my negative binomial random variable, because this is the success probability. Okay, and r is the other parameter of my binomial. And from here, it's of course quite straightforward that the expectation is r times the expectation of the optimistic geometric, so it's r times 1 over p. And again, because of independence, the variance of negative binomial is going to be r times the variance of the individual geometrics, so r times q over p squared. Okay? We are going to see a way to prove this directly later on in the unit. But for now, at least from this probabilistic point of view, from this observation of independent geometric weighting times between successes, one can easily conclude the mean and the variance of negative binomial. Okay. Now, let me proceed to the next distribution, and that is going to be the hypergeometric. So the hypergeometric random variable is a little bit funny. It's not that common, so I'm not sure how many of you have seen it before. Hypergeometric. It has so many parameters and it has so many constraints that instead of starting to write up all the parameters, I'm going to tell you a tale. I'm going to tell you the story immediately. So the story is this. There are n deer in the forest. Okay? And m of them, m of these deer are tagged. So we tag m of them, then we release those m back into the forest. We assume that they mix well with the population of deer. We assume that the number of deer is constant, so there are no deer born and no deer dying or disappearing. And later on, well mixed, so independently of which were tagged, n random deer. Let's put this in parentheses. N random deer are captured. And now x is going to be the number of tagged deer, among those captured. Okay? So what is the number of tagged deer among all of those which are captured? That's x. Now, x obviously has a lot of restrictions. It cannot be larger than m. It cannot be larger than n. But it might not be too small either, because if we tag a lot of deer and if we capture a lot of deer, then maybe there must be a big intersection between the two. So there are restrictions on x in all directions. I'm not going to list those. I'm going to straight away go for the mass function of x. What is the probability that x equals to k? Okay, so what is the sample space of this experiment? Well, the sample space is that we're going to capture n individual deer. So I'm going to say that the sample space is n combinations of capital N deer, and there are capital N choose little n many of those. Okay, so this is all the possibilities to capture n deer out of capital N with no respect of tagging whatsoever. But then the event x equals to k means that out of the tagged deer we have to capture k. So out of the m tagged deer we have to select which ones we're going to capture, And then there is a remaining n minus m deer, out of which we have to capture the remaining n minus k. So it's going to be m choose k times n minus m choose n minus k. Many ways of capturing exactly k of the tagged deer and then the remaining n minus k of the non-tagged n minus m deer. Okay? So the binomial coefficients, notice that the binomial coefficient m choose k is going to be 0 if k is negative. Okay, that's not very interesting, at least not for the first term. But it's also 0 if k is larger than m. Okay, so this restricts already, if we write this up, that restricts x, the possible values of x with positive probability, to something non-negative and not larger than m. But then the same happens to this binomial coefficient. So as soon as n minus k would go negative, again the probability is 0. So k cannot exceed n. But then as soon as n minus k goes above n minus m, again we have 0. So whenever n minus k would exceed n minus m, again we have 0 for the probability. And these are actually the restrictions for x. So if you look at all these binomials where they become 0, they exactly give you the correct restrictions on the values of x. Okay? So that's why I'm not going to bother to write out all the conditions. You can actually just read them off from the binomial coefficient. And I'm also not going to write out all the parameters. There are 3 parameters in the problem: capital M, the number of deer, m is the number of deer tagged, and little n, the number of deer captured. So let me write this out again, just copying the previous formula. And then let me kind of reformulate the problem. So we have n deer in the forest. We have a random subset of m of them and an independent random subset of n of them. So recall that here we assume that there is a good mixing. So whoever were tagged, they mixed well with the population of deer, and when we capture again n of them, we don't know which are tagged. So these are completely independent samples of the population. And if you look at that, if you look at what x is the size of the intersection. So what's really going on is that you have an object of a set of n different objects, a subset of size m, a subset of size n, and we're looking at, these are independent and random, and we're looking at the size of the intersection. That's what hypergeometric really is. And now if you carefully think this through, then you end up with a very funny identity. This probability then must be the same as n choose k, big N minus little n, over choose m minus k divided by big N choose little m. Okay? Homework for no marks. Check that this is equal. You can check it 2 ways. You can actually write out all the factorials and you see it's going to be equal. Or you can just remember what I said. It's just 2 random subsets of m and n. And really what happens from here to there is that I swapped the role of little n and m. And if it's 2 random subsets, the role of these 2 random subsets is symmetric. So it's actually okay to swap them. Then it must give the same probability. And it indeed does. Okay. To find the expectation of the hypergeometric, one can look at indicators. I'm not going to do that here. The expectation of hypergeometric will turn out to be m times n over n. And you can just find this as the indicator of a particular deer being both tagged and captured. And you can also find the variance this way, but it's a long, ugly formula, so I'm not going to bother writing it out. If you're interested in that, just look it up. Okay, how do we know that this thing is a mass function? Well, that's again not so easy, but if you look at the probabilistic definition of what we did, then it's pretty clear that there must be some number of tag there. So if you sum this k up for all possible values, of course this probability must sum up to 1. And we're going to actually use this, but a direct combinatorial proof I'm not going to provide here.